Welcome everybody to our 23rd Reiss lecture. It's the 23rd, yeah, unless time it's counted, but it's right. So you see, it's a long tradition, and so so not everybody will remember Ed Reiss, probably actually almost nobody in here. So he was one of the founders of our department. He did a lot of seminal work in bifurcation theory and flattering. So there's some fluids which, however, are today not relevant. They were relevant yesterday if you came to the other talk that Peko Hosoi. Anyway, so I'm very happy that we managed to have Peko Hosoi giving here that lecture. She is in the mechanical engineering department. She's the Papalardo Professor for Mechanical Engineering at MIT, and she's also in the math department. And also now I can read it off. That's good. Institute for Data Systems and Society. So she is, and as she pointed out, she founded the sports lab, which will be featured importantly today. She has a long list of accomplishments in fluid dynamics. She is APS Fluids, the two fluid division member of the fellowship of the Fluids, IPS Fluids division. You know what I mean. And, what's more important, she also got the Corson Fluids Prize, which is sort of a step up from just being a fellow. And she also, if you were at the talk yesterday, you will not surprised. She has a lot of awards for teaching excellence. And so I didn't say that yesterday because I wanted to surprise you, but now it's so anyway, I don't want to waste more time. I'm very happy that you're here and you'll tell us about stuff we usually don't hear about. And so that's very exciting.
Thank you, Herman. Thank you for inviting me. So like Herman said, my background is fluid mechanics, and there is no fluid mechanics in this talk. So at some point I got interested in data and sports and applied math. So I'm going to give you 3 stories about data, sports, and applied math. I'm going to say I'm 90% confident I can do all 3 in an hour. So if I have to cut it off, I'll cut it off. So I guarantee to probably 3 short stories. All right. So here's short story number 1. So let's see if I can. So short story number 1 is about basketball. So this is basketball. This is about measuring court sense and decision making in basketball. So the question we were interested in here is that when you talk to the professional sports teams in the NBA or in the NBA, they are measuring everything they can measure about their athletes. Like they are measuring how high they can jump, how much they can bench press, how fast they can run, anything physical that can measure, it's being measured. Then you talk to the coaches and they say, well, yes, all of these measurements are great. These are very useful. But, really, when we are selecting people from the NBA, what may be even more important is what is their court sense, or what are their game smarts when they're on the court, and how can we start to measure those mental capabilities of the athletes in addition to the physical capabilities of the athletes? So we said, well, one of the interesting things about sports is that every decision you make results in some kind of an action or an inaction, right? You're basically deciding to do things on the court. And because all these decisions manifest as some kind of a physical action, there should be some signature of your decision-making capability in the tracking data, right? So this is what we're going to do. We're going to say, can I pull some kind of metric about decision-making from the tracking data? All right, so here's the tracking data. So I don't know if you may know this. So in every NBA arena, there's a system of cameras in the ceiling. It was originally put up by Second Spectrum. It's now run by a new company called Hawkeye. But they basically track the XY coordinates of every athlete and the XYZ coordinates of the ball at 25 hertz for every game that's been played in the NBA since 2014. It's a huge data set. I think when I made this slide, I think there's even more now. So we had something like 15 million shots, 15 million possessions, 30,000. So every time you dribble, that's an event. So we have a record of everything that's happened in the NBA since 2014. Okay, so that's the data set. It's a huge data set. We have to give a shout out to Google because we couldn't have done this without getting access to Google Cloud. So they gave us some processing power and memory to actually look at all this data. I'll say one other thing about this. So now that Hawkeye has taken over, they not only have center of mass data, they have skeletal data. So now they have an optical system where for every athlete, they have about on the order of 20 points. So they have your elbow, your shoulder, your hips, your head, and for every athlete at 25 hertz in every game that's being played in the NBA. So that's happening in NBA, and it's also happening in FIFA. So if you're interested in soccer, you can also now get, well, I don't know if everybody could get this data, but it is being collected for all of the World Cup games in soccer. So skeleton level data. Okay, but we didn't have that at the time. We had center of mass data. And so we asked the following question. We said, okay, suppose I look at a game of basketball and I freeze the game at some point, right? So I have some guys on offense and I have some guys on defense and some guy with the ball. And this guy with the ball, there's basically three things he can do. I mean, we could get more granular, but there's basically three things he can do. He can shoot the ball. Okay, and if you shoot the ball, there is some probability that he scores. Okay, so PS is the probability that he scores. PB is the ball handler, so it's the probability that that guy scores. And the probability that he scores depends on what else is going on the court, right? So it depends on the positions and the velocities of all the other players. So it depends on whether this guy's here and whether he's running at this guy or whether he's backing up or anything like that. So there's some probability that depends on what else is going on. The other option is he could pass the ball. And there's some probability that this pass will be successful. So he could pass to that guy over there. And again, the probability of success of that pass depends on the positions and velocities of everybody else on the court. Okay. And the other thing he could do is nothing. He could just keep the ball. Okay. So that's kind of what you do. Now, because I just told you I've just got a boatload of data on this, like a giant boatload on data of every shot that's been taken in the NBA since 2014. I can just put this into my favorite machine learning algorithm, pick whichever one you like, and learn these probabilities, right? So that's what we did. And I think it's, I mean, there's so much data, it doesn't even matter which is your favorite machine learning algorithm. So the student who worked on this, Ivan Jutumolia, just did a neural network. It's a pretty straightforward neural network. We have a paper, you can look at the details, but you don't have to do anything fancy. You just learn the details. So now, if I have the positions and velocities of people on the court, I can tell you with some level of confidence, what is the probability that if he shoots now, that it goes in, and what is the probability that a pass to somebody else would be successful. Okay, so I know those probabilities. Now, we're going to define something that is called the expected possession value. Okay, and the expected possession value looks like this. You say, I'm going to say, so what is the probability so this is the expected possession value if he passes to player J. So let's say this is player J. So this is the expected possession value if the probability that the pass is successful times the probability that the shot is successful times the value of the shot. So is it a 2-point shot or a 3-point shot? Okay, and so for every pass on here, I can calculate what is the probability, what is the expected value of that shot. And now now I'm done, basically, right? Because you can do the following. So imagine I take every possession in the NBA, I take one possession, I freeze right before that guy took the shot. Okay, I'm now going to calculate the expected possession value if he took the shot. And I'm going to calculate the expected possession value if instead he passed this guy to that guy. And if his expected possession value is the highest one, then he made a good decision. If there was a better option, if somebody else had a higher expected possession value, he made a bad decision, right? And you can just go and you can do that calculation. Yes.
How about you pass it to someone who passes it to someone else?
Yes. So great question. The combinatorics of that rapidly gets very, very large. And so for the question we were asking which is, are you making a good decision right now? This got us what we need, and I'll show you why. But that's the question I really want to do. But I mean, actually, wait, you know how to make things efficient in computing. Tell me how I do this without the combinatorics being unmanageable. But and one of the reasons it becomes unmanageable is because this is a short time thing. So in the time it takes for him to pass to that guy and that guy to take shot, people don't move very much. So you can kind of say, okay, given this configuration, what is the probability of all that happening? Okay. Yeah, Mike.
So you're not distinguishing between the position, whether it's a center, a
Correct.
guard, or a forward?
Correct. And when we do it this,
1/3 then.
yeah, exactly. Yeah. So we currently did it for just an average basketball player. And it turns out, again, for the, and I'll show you in a minute, that for decision making, it's kind of okay. And I think that's because the centers are usually where they should be and the guards are where they should be, et cetera. I think you could do better. So I think it would be probably intractable if you did it by person. Like, for example, Steph Curry, you can pass to Steph Curry anywhere in the court and he can take a shot and it's going to be a good shot. It's fine, right? But I think the other thing you could do is you could actually bin by free throw shooting percentage. like just make 5 bins and say, are you a good shooter, an average shooter, or a poor shooter? And then retrain the neural network based on that. And I think we would do even better than what we're currently doing. Yeah. But we do pretty well with this. You'll see. Good. Good. This is good. Okay. So, so next one, I'm going to show you a basketball possession. Okay. So I'm going to play this possession for you. And then after that, I'm going to show you what the computer sees. So for those of you who are familiar with basketball, I want you to watch this and tell me if you think this is a good possession or a bad possession. For those of you who are not familiar with basketball, this is what basketball looks like. All right, so here we go, basketball. So we worked with the Spurs, so we had to pick Spurs possession. The Spurs are in the white jerseys playing against the Nuggets, and they're moving the ball around nicely. Passes back outside, he takes a 3-point jumper. Nice. Okay, so that seems all good. All right, so there's the possession. Okay, so now let me show you what the algorithm sees. So on the top here, let me just get this going. So on the top, what you've got. I don't know. Okay, so on the top, this is the tracking data just directly from Second Spectrum. This is the optical tracking data that they get from their cameras. The red or the orange guy over there is the ball, so you can see who has the ball. The guys that have a number, these are on offense. The guy with a little X is a defensive player. Okay, and I'm going to let this go for a little bit, and you'll see once the ball goes across the midcourt, you're going to see some lines come up on the bottom here. Okay, so this here is the expected possession value that I just defined. So if I freeze at this point, for example, let's think about this guy right here. So this is Forbes. This blue line here, which goes with that blue dot, is what is the expected possession value if at this point you pass to Forbes and he took a shot. Okay, so you can see that, do that for every guy in the court. This red line, this is the average points per possession. So you don't want to take a shot unless you're above this line. Right, so if you're making good decisions, if you go above this line, you should take a shot. All right, so here's what the computer sees on that possession I just showed you. So everything's going around nicely. Yes, ball's being passed around a little bit, and nothing and oh, something happens, and they don't take the shot. They take the shot here. So in fact, that was not a terribly good possession because they missed a really big opportunity. Right, so this is almost 2 points. This is like a guaranteed 2 points that missed. Okay, so now let's go back. Did anybody see those 2 points? Okay, so now let me show you what's in the video. Okay, so here's the video. And I'm just going to grab this to move it forward a little bit. So let me show you where that spike happens. So you're running right here. Okay, right there. You see that big guy running when he's hard around the basket with that open passing lane? Right? I mean, that's a guaranteed 2 points. And the thing that I love about this is I never said to this algorithm, look for the giant guy under the basket waving his arms around to the open passing lane. I never said that. I said, here are a bunch of different possessions in the NBA. Please tell me if I missed something. And it said you missed something, right? So the coaches love, and one of the reasons the coaches love this is that basketball, there are so many games played per week that they have like 10, 20, 30 hours of tape that they have to watch to know what's going on. And we can now tell them, actually, you don't need to watch all those 30 hours. I can tell you exactly when interesting things are happening in these possessions, and I just give you a list. And you can just watch that tape first. And then if you want to watch more basketball, you can watch more basketball. But this way you'll know, you won't miss any of those. Okay, so that's the way the algorithm works. So one other thing you might ask is, okay, I probably picked a good example for you, right? Obviously, that's what you always do. But you can ask, how many additional points could a team score if they capitalized on all of their missed opportunities, right? So I just go through a whole game, and on average, I say, how many times, what's the difference between what you actually did and what the expected value would have been? And you find that on average, teams are leaving almost 30 points on the table, which is a huge amount of points. Now, not all of these are valid, right? Because a lot of this would be, okay, I have a game plan that I meant to do something else, right? So that's totally fine. But, let's suppose you could capitalize on a third of these. Right, a third of these, like I'm always missing the pass over there, right? I mean, that's 10 points. And the difference in 10 points per game in the NBA is the difference between being at the top of the rankings and the bottom of the rankings, right? So there's a lot here that if you point them out, that coaches and players can focus on. Okay, and then the next one, of course, you want to know who are the good decision makers in the NBA. So every dot here is a person. And this axis, the vertical axis means nothing. It's the horizontal axis. It's the only thing that makes a difference. And this is the missed opportunity rate. So how many times did I go above the red line and you did not do what you should have done? What is the fraction of the time you did that? This is for point guards, shooting guards, fires, et cetera, et cetera, et cetera. And I'm not going to label all of these for you, but I will label a couple of them, partially because it's proprietary data, but I'll label a couple of these for you. So here are some of the good decision makers and some of the bad decision makers. And I will tell you that this is data from January 2018. So we took all of the games in January 2018. Okay, so first of all, okay, Steph Curry, Dame Lillard, James Harden, great. Okay, good job, everybody. You're making good decisions. The interesting ones are over here. So in January 2018, Russell Westbrook was on track to get a triple-double, but the OKC was not on track to be in the playoffs. So at that point, they didn't care if they were winning games. They were just trying to get Russell Westbrook his triple-double. So they were not making decisions to win games. They were making decisions for Russell Westbrook to take all his crummy shots so he could get his triple-double. Okay, so that comes out in the data. The other one, if you're following basketball, Ben Simmons had a rough 2018, made a lot of bad decisions, as did Lonzo Ball. It's a tough season for him. So it does pick out kind of the people who are fine, who are making great decisions, and the ones who maybe could use a little bit of coaching. Yeah.
I think you said this, but what's the units of missed opportunity rate?
Yeah. Oh, yeah, the missed opportunity rate. So first of all, I should have covered up these numbers because these have been normalized, but it's basically the fraction of times that you have the ball that you make the wrong decision, like that you made the wrong decision. Yeah.
It's not 100% for Lonzo Ball.
It's not 100%, exactly. Yeah, this is just exactly. This is normalized by law. Yes, correct. Thank you. Yes, but yeah.
Is the standard deviation on these averages significant? Because you could imagine players that always do the wrong thing or the right thing, and you could imagine players that sometimes are great, sometimes are
yeah. Actually, that's a great question. We have not looked into that, and that's actually a really interesting question. Like, especially if you're training new players, because ideally what we would like to encourage coaches to use this for is to say, we can tell you when people are making mistakes, and you can then sort that. And these are the times they did not make a mistake, and these are the times they did make a mistake, and patterns to that. Like, I never see anybody over there, but I'm good over there. Right? That's actually really useful information. So we haven't dug into that, but I think that's when things get really interesting. Yeah.
How do you update, because you can imagine a strategy of the game changes over many years, right?
Yes.
So how do you update the training in the data?
Yeah, great question. So the tracking data we only have since 2014, and 2014 was after the 3-point revolution. So we don't have the data, the tracking data before that. So the game has been fairly consistent in the period that we had the data, and we trained it on. I have to think. It wasn't the whole data set. It was maybe a couple of years. So I think if you had a sliding window and trained on that sliding window, you'd probably be okay. Yeah.
Can you do a reverse, like just look at people who are not handling the ball, and then just can make a decision whether he should screen or run to a new location and increase the expectation?
Yes. This is what we really need to do. So the question here is, what about off ball? Right? Can I make a judgment on how well people are positioning themselves off ball? That's the $1 million question. And that one's a little bit trickier because, so the nice thing about when you have the ball, you have a very clear metric on, did I do the right thing or not? Because either the ball went in or it did not, right? If you're doing an off ball screen, it is not immediately obvious what the result of your action was. So first I'll say two big open questions. One is, how do we do something like this for off ball actions? And the second is, how do you do something like this for a game like soccer where you're not scoring every 24 seconds? Right here, I had so many shots that it was just easy to learn. In soccer, where you only take a couple of shots per game, it's much harder. And so instead of using the score as the thing you have to train on, you have to figure out what is another metric for a good position in soccer. Like if I showed you a shot of a screen at this time and a shot of a screen at this time, you have to tell me which one would you rather have and why, right? And so that's a lot harder, but I think that's the big, interesting open question now that we know it kind of works. Great. Yeah.
One question. So here the neural network was trained in order to forecast the probability of success over decisions that were taken by the players.
Correct.
And is there a possibility that there might be some selection bias, meaning that maybe the player has a wider information set that
Yeah.
doesn't just include position and velocities? Like, let's say I have a stomachache and so I
Yeah.
better that person on the left.
Yes, yeah, so there is variance in our prediction. We're like 80% correct, right? So the 20% is I have a stomachache or something like that. Yeah, so absolutely true. The other thing I would say is that there's an interesting question about bias on learning the passing probabilities, because it is very rare that you make a bad pass in the NBA because you just don't do it. And so we're basically training on a bunch of successful passes, which means that the algorithm learns that every pass you make is successful, right? So you have to be careful about that, and you have to weight more heavily the bad passes to make sure that the algorithm learns actually you can screw this up. So so be aware that you can screw this up. Yeah, yeah, great, great. I'm going to go on to short story number 2. Nice questions, everybody. All right, so here's short story number 2. So short story number 2. This came to us from the NFL. So the NFL called us at some point and said, is it okay to have sports fans in stadiums during the pandemic? And here's why they called us and asked us that. You may remember during the pandemic, some of the stadiums were open, those are the orange ones, and some of the stadiums were closed. And the way they make the decision as to whether or not, and by the way, games were played in all of these. It was just depending on, but some played with no fans and some played with fans. Okay, so, but games were played in all of these. And so the way you decide whether or not to open the stadium is it's the local stadium ownership, which is basically the team, meets with the local government, and they have a conversation, and then they make a decision whether or not to open the stadium and what the rules are going to be. So everybody opened them under different rules or just didn't open. Okay. So so there was a group, not us, that did an analysis on this, and they published a paper, and they said there's been an increase in COVID spikes in cities where the NFL opened their stadiums. And the NFL called us and they said, is this true? This is bad. If we did this and this is bad, that's bad. So can you please take a look at the data and tell us whether or not this is true? And you can already see that there's kind of a problem with, so what they did is they just looked at the COVID cases around games when somebody opened and then just counted the number of spikes in COVID cases. Okay. And you can already see that there's kind of a problem with this because the stadiums that were open are in places like Florida and Texas. And the stadiums that are closed are in places like New York and Massachusetts and California. And so there were a lot of differences in COVID policy around that time, besides whether or not you opened the stadium. So yes, maybe the spike came from opening the stadium, or maybe they came from something else, right? And the other study did not correct. Okay, so we said, okay, yes, we can do an analysis on this. So here's the data that we have. So the data we had is we have the locations of all the stadiums. So we know the county, this is a county map of Texas, by the way. So we have the county that the stadium is in. We have the dates that the stadium first opened to fans. So many of them did not open immediately. They waited like Houston waited until October 4th to open. And we have the famous data set, which many of you have probably seen, which is the New York Times data set, which gives you the number of COVID cases by county, right? And they have this beautiful GitHub site, and you can just download the data. It's great. Okay. So we have this. So the thing that happened right around this time that we got this problem is I was introduced to something called synthetic control, and synthetic control changed my life. This is one of the few things I've learned. Like, I went to a workshop that was put on by one of my colleagues, and now this has completely changed my view of the way you can actually use data in the world. Okay, so here's the way synthetic control works in this situation. So the ideal experiment you would like to do is the following. You would say, okay, I'm going to measure the COVID cases through the summer of 2020. Then I'm going to open the stadium in Dallas. And then I'm going to measure the COVID cases after that. So I have some timeline of COVID cases. Then I'm going to get in my time machine and I'm going to go back to the beginning of the summer and I'm going to measure it again. And now I'm going to not open the stadium and I'm going to measure the COVID cases and I'm just going to look at the difference. That's the perfect experiment, if I could do that. And the problem is the time machine. Okay, so the question is, where do you get the time machine? And what synthetic control does is you say, okay, well, I don't have a Dallas that doesn't have a stadium in it, but I have all of these other counties that don't have stadiums in it, and some of them look kind of like Dallas. So what if, instead of Dallas, what if I take a linear combination of the stadiums that are similar to Dallas and use that as my not open stadium, and then just open the stadium in Dallas and compare the two? Okay, so that's the idea. So that's synthetic control. So let me show you how it works. Let me give you a little bit more math on how this works. By the way, I'm gonna skip between different NFL teams in the hopes that I hit somebody's favorite team. Okay, so we're now out of Dallas. We're now in Minneapolis. Okay, so this is Minnesota Vikings. Actually, it's not Minneapolis, it's Hennepin County. Okay, so this is the number of COVID cases in Hennepin County, and this is when they opened the stadium, right here. And then you can go over here and you can say, well, I'm going to look at all the other counties in Minneapolis, which had similar policies. So there's Polk County, there's Fairfax County, there's Brown County, and I can go to the New York Times data set and I get some curve from that. And this is where the stadium opened for all of those. Okay. And now I'm going to say, okay, I'm now going to build a synthetic Hennepin County, which is maybe 36% Polk County, 54%, I made these numbers up, 10% Brown County, but I'm just going to do a linear combination of these guys to make a synthetic version of Hennepin. Okay? And the way you do that is you say, okay, this S, so this is the actual measured number of COVID cases. This is my synthetic approximation of the number of COVID cases, which I build out of a linear combination of these other basis functions. Okay, so I do that.
Pre-stadium opening?
Pre-stadium opening, yes, exactly. Yes, perfect. And so see, pre-stadium opening. Color that. Perfect, yes. So you find your alphas, you minimize this, you minimize the difference between the synthetic county and the real county pre-stadium opening, and then you just run forward. Okay. Okay. Yeah.
You get multiple minima.
You get perfect question. I didn't even plant this question. Okay, so that's exactly right. So you have a problem here because these are not orthogonal, right? But I can make an orthogonal set of basis functions, right? So instead of actually using Pope, Faribault, and Brown, what I do is I actually make a matrix. So these are all of my donor counties. Pope County, Faribault, Brown County. This is time in this axis, so this is number of days. Okay, so I now have, this is just all of my data. And I'm now going to find the set of basis functions that spans that space by just doing a singular value decomposition. Right? So I do my SVD, and if this is going to work, this should be a low rank matrix. Right? Because if it's not a low rank matrix, then each of these guys is different, and then I can't use them to predict anything. Right. But if it's low rank, that tells me there's some underlying structure, which is coming from the way diseases are transmitted, the way people use the subway, the way people go to their birthday parties, right? I don't know what it is, but there is some underlying mechanism that is constraining the way the disease progresses, which is hidden in this data. Okay, so if that's true, this should be low rank, and it is. So this is the normalized magnitude of all of my singular values, and you only need to take like 5 to capture everything. Okay. So to your question, if you do this, then there is one minimum. If you do not do this, then you're in trouble. Yeah. Good. Okay. So I find my alphas and I do it. All right. So let me show you how this works. So this is Cincinnati Bengals. Okay. So Cincinnati Bengals, this is the number of COVID cases. This is game day. Okay. This is Hamilton County. So this is measured. This is red is measured, and blue is my synthetic county. Okay, and I'm going to let you stare at that for a minute. So this is pre-intervention. This is post-intervention. There's some difference between them. One thing that's nice is you can see they track each other for about, I don't know, 2 or 3 weeks, which is usually, if you look at the New York Times database, it takes about 2 or 3 weeks to see sort of the results of an event like Christmas or New Year's. You suddenly see spikes 2 or 3 weeks after that. So if something happened, this is when you expect to see it. Okay, but now I've given you enough time to stare at this, and so hopefully you have now some of you come up with the fact that there's something very weird about this. And the weird thing about this is that the synthetic county, which is the one where the stadium did not open, has more cases than what was actually measured. So this would suggest that opening the stadium actually helped. So we'll pause on that. I don't know if that's actually true. Let me show you what all of them look like. Okay, so this is what all of them look like. These down here are the ones where fans were not allowed in the stadium. So if this is working, there should be no difference between the red and the blue ones, because my synthetic county has no stadium. There's a bunch of counties with no stadiums, and the red one has a stadium, right? So these should all be exactly on top of each other. Okay, these are the ones up here where the stadium opened, and so this is where I'm looking for a difference between the red and the blue curves. Okay. So I'll let you guys stare at that. I'm going to show you, I'm going to give you a summary of all of this. I will also point out that Green Bay is a disaster, terrible data taking in Green Bay. And I'll tell you why that is in a minute too. Okay. So now what I'm going to do is I'm going to plot for you this delta T for each of those stadiums. Okay. So I'm going to do it for the stadiums that remain closed and the stadiums that opened, and delta T, I'm going to plot it as a function of days past opening, right? So I'm going to delta T at day 1, day 2, day 3, day 4. Averaged over all of the stadiums that were closed and over all the stadiums that were open. Okay, so this is for stadiums that had no fans. This is that delta T, and nothing happened. So this is good. This is good news, right? Because this is my control, right? My synthetic stadium has no fans. My real stadium has no fans. The difference between them to the margin to whatever statistical significance I can get, there's basically no difference between the two. Okay. So the control seems okay, right? I can actually replicate with my synthetic stadium what I would expect. All right, so here's what happens in the stadiums where you do let in fans. Okay, so it's still to within the margin of error, basically 0, right? I mean, I can't tell the difference between these. But this is 0 right here. Above this line, I have more cases than in the synthetic counting. So this is bad. This is opening the stadiums was bad. This is fewer cases. So this is opening the stadiums were good. So there is a small bias in this data, which seems to be coming down this way. It's not statistically significant. So the first answer to the NFL is you did not blow anything up. It was fine. Okay. The second question, though, you could ask is there are some counties where it does look like there were fewer cases than you would have expected. When you open the stadiums. So can we think about, okay, why might that happen? And there is a reason why that might happen. And the reason behind that is in this guy right here. So I'm going to come back to this guy. This guy is a model citizen during a pandemic. Look at what he's doing. He is outside. He is wearing a mask. He is like 10 feet from the other guy who's over there. Like, this is perfect behavior right here. And if you think about it, now look at this guy and imagine if he was not at this football stadium, what would he be doing? Right? And so the question is not, what would the people in the football stadium, what would the number of cases be if these people disappeared off the face of the earth? Yes, we would have less COVID cases. It's what would the COVID cases be if they were doing what they would have done if they were not in the stadium? This guy was probably going to be watching the game, I'm guessing. Maybe at a sports bar, maybe at a friend's house, maybe he was watching it by himself, but he doesn't look like a watch by himself kind of guy. Right? So one of the things that opening the stadiums did is that these are obviously cities where there are a lot of football. These are football culture cities like Pittsburgh, right? And so it gave people like this an option to be outside and masked and separated during the game. Okay, so it's feasible. It's feasible that signal was actually real. All right. So now there's one more question that you should ask though, which is to say, okay, Peko, you just told me that you didn't detect anything. So maybe that is because there was nothing to detect, or maybe it's because your method is really crappy and didn't detect anything. So the question you can ask is, are there ways we could check whether the method is any good? So the first thing you do is you say, okay, can I check if the method is sensitive enough to detect something where I know there's a signal, right? So is there a known super spreading event that we can check? And yes, there are a number of them, but probably the most famous one of them was the Sturgis motorcycle rally. Okay, so the Sturgis motorcycle rally, there's many papers written on this. I think there's an estimate that this cost something like $12 billion in healthcare costs because there were people from 2/3 of the states that came to Sturgis, which is a small county in South Dakota, all caught COVID and then dispersed. Okay. So the question we said is, all right, can we detect the super spreading event that happened in Sturgis? And the answer is yes, it does come out. So now you can see the red curve is above. This is noisy because the population of Sturgis is not very big. But 21 days after, there was a 43% increase over what you would have expected after the motorcycle route. So yes, for known events, we can detect it. The other thing you can do is you can say, so this is not a proof, but this is just kind of like a check to see if everything is consistent. So we could say, okay, in the counties where we see things growing, does it correlate with other things that we think might correlate with number of COVID cases, like population density, or like the county next to me had a bunch of COVID cases, so next I should get a bunch of COVID cases, right? So are there any correlations like that we can check for? So we can do that. So what we do is, again, we make our nice basis functions. And before, all I did is I used those basis functions to reconstruct the stadium counties. But now I can use those basis functions to reconstruct any county, right? I can just pick any county and I can say, oh, I'm going to just make that county as a sum of whatever basis functions I've got. I cut it off at some low dimensional representation. And so now every county can be represented by this vector of alphas, right? So let's say I pick five basis functions. Every county has a string of 5 alphas, which describes what their COVID cases look like. Okay, so I now have every county that in some low dimensional space. I can put them in that low dimensional space. So here's county I, here's let's say I took 3. So here's my 3 basis vector, county I is here. And I can look at the distance of county I to different other counties, right? So I can just see which counties are close to one another. And so what I'm looking for is what are the counties that are close in this COVID case space? Are they also close in things like population density? Or are they close in other spaces that you think might be related to how COVID is transmitted? Okay, so this is the distance in this COVID case space. And I'm gonna plot for you the distance of all of the counties in Ohio, now in Ohio, the distance from Cuyahoga and Mercer. And we'll tell you in a minute why we might pick Cuyahoga and Mercer. So I do that, and I just colored this in. So this is a map of Ohio where every county is colored by the distance between Cuyahoga County and Mercer County in my alpha space. So the only data in here is the New York Times COVID data time series. That's it. There's no other data in. This is just New York Times COVID time series. Does anybody recognize this map? It's the political map. That is the 2020 electoral map of Ohio. Okay, and in fact, so first you look at this and you say, oh, well, maybe I just pulled out the big population center, so this is actually a population density map. But it turns out, no, the thing that is most predictive of how COVID spreads is the political leanings of that county, right? It is more predictive than population density. It is more predictive than whether or not your neighboring counties have, it's not geographic distance, it's not population distance. The thing that is most predictive is how that county voted in the 2020 election. If to look at the time series. Okay, so and that's as far as, so the NFL didn't ask for that, so we didn't go any further on this. But I think there's actually something really interesting in here, and there's interesting ways to look at this data, which we haven't done. But I just wanted to put that up as a teaser for anybody who might be interested in looking at that kind of space. Okay, yes.
Hi. When you looked at the NFL data, did you take into account which stadiums had domes and which were open?
Oh, great question. So we did not. I think a lot of the domes were open during COVID. I don't know if that's 100% true. But the other thing that's important about the NFL data is that the people in the stadium are not necessarily the people in the county, right? Because they can come from different places. So one of the things the NFL gave us is they gave us a list of zip codes. So they said, which zip codes is everybody coming from? So we actually, for a stadium county, we counted that as, at least 10% of the people were coming from that zip code. For a non-stadium county, we said, no, basically nobody comes from that county. And then there's kind of a middle layer, which we just threw out because I said, I don't know if this is a stadium county or not a stadium county. Yeah, so you do have to be a little bit subtle about counting who's a stadium county and who's not. Yeah, good. Other questions about NFL? By the way, synthetic control. This when you do it this way, when you do the singular value decomposition, it is provably robust. So it is really, really an incredible tool if you have natural experiments and you don't have a randomized control. It's basically a way to get you as close to a randomized control as you can within a robust way if you can't do the experiments, which are often really hard to do and expensive. I mean, I can't pick which stadiums to open, so. Great. Okay, I'm going to go on to, this is good. Okay, I'm going to be able to do this. This is perfect. I have 20 minutes to do my last short story. This is my last short story. So my last short story is Luck and the Law. And so this is a story about fantasy. How many people here play fantasy sports? Anybody? Yes, good, 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 excellent. I play fantasy football. I crush my 8-year-old nieces. And so this is a project that was brought to us by FanDuel, which is one of the online purveyors of fantasy sports. So first, since only a few people play fantasy sports, let me tell you how you play fantasy sports. There's a couple of different formats, but this is the one I'm going to talk about today. So the first thing you do is you call like 12 of your friends and you form a league. Okay, so you call your best friends, you say, we're going to play fantasy sports. Then you draft your team. And so in football, for example, you get to draft. I'm going to tell you what draft means in a minute. 9 players, so a quarterback, a couple of wide receivers, running backs, a tight end, defense, and a kicker. So you draft these different positions. And what draft means in that sense is you go to some online website that manages these games, and each of them, and on this online website, they list all of their players. Okay, all of the players, and these are real players in the NFL, so they list real players, and you get the name, you get their position. So it's a wide receiver, so I could put Larry Fitzgerald in the wide receiver position, and they have a fake salary. Okay, and this fake salary is in the game. You are given $25,000 of fake money, so it's imaginary monopoly money, and you can spend those $25,000 to buy your players to fill out your roster. Okay. So you can already now see what the object of the game is, right? This is an arbitrage game. This is I am looking for players that have been undervalued by whatever algorithm this guy has made. I don't know what the algorithm is, but I'm looking for players that are undervalued so I get more bang for my buck when I'm spending my $25,000. Okay, so that's the game. Okay, so you then you draft your roster. So I draft a bunch of players, and then step 3 is you watch football. Okay, so you watch football with your friends, and for example, if I don't know who I've drafted here, but if whoever this guy is, if he scores a touchdown, then I get 7 points, right? If I'm playing against Mike and his quarterback scores a touchdown, then he gets 7 points, right? So we get points based on whatever the real athletes are doing in real life. Okay, so you kind of have to predict who is going to get passes, who is going to do well on whatever weekend you're playing. Okay, so that's the game. Pretty good with the game. So the game, this is sort of a recent history of fantasy sports. So this was 1990, this is 2010. I need to extend this. It's continuing to go up. This is the number of players in the United States of people who are playing fantasy sports, right? So at this point, it was 60 million, and now with DraftKings and FanDuel, it's higher. Like there's hundreds of millions of people playing these games. And you can see that something happened kind of around maybe here. Things started to go up really sharply. And what happened here is there were 2 big players that came onto the game. One was DraftKings and one was FanDuel. FanDuel was the one who called us, who had their question. And these are the online game providers. So they're the ones who are writing these algorithms and allowing you to go and play online. And there were 2 important things that they did that caused this. Okay, the first thing is they got rid of you have to get 12 of your best friends to form a league and convince them to play with you. You can just go onto this site and play with somebody else, like random person in Tennessee might want to play against you, right? So you can just go in and play. The second thing they did, which was probably even more important, is they allowed you to play for money. So there are a couple of different kinds of games that you can play. One is one's called a 50-50. So there's a bunch of people who play, and you pay $1 to play. If you score in the top 50%, you double your money. If you score in the bottom 50%, you lose your $1. Okay, so you just have to be better than half of the people playing. So we have data on 50-50s. The other thing that happened around this time was that Congress passed something called the UIGEA. And the UIGEA is the Unlawful Internet Gambling Enforcement Act. Anybody heard of the UIGEA? Okay, no poker players in this room. Okay, so the UIGEA so it states the following. It says, you are not allowed to transmit money across state lines using the internet that you won by gambling. Right, so gambling money cannot be transmitted across state lines using the internet. Okay, so right around this time, DraftKings and FanDuel started taking off. A lot of money was exchanging hands. People were playing games. And so there were a lot of attorneys general that said, hey, this looks like gambling. Maybe we should be shutting this down, which is why FanDuel called us. Okay, so here's what the law actually says. Okay, so let's dig in a little bit more to say, okay, is this actually gambling? So this is how the law defines a bet or wager. There's important words in this. So the first thing is a bet or wager does not include participation in any fantasy or simulation sports game. Okay, so the first thing that you learn in reading this is that there was somebody in Congress who had a fantasy football team who was not going to vote for this if they couldn't keep their fantasy football team. Okay, so fine.
You mean a lobbyist.
Exactly, or maybe lobbyists. Exactly. Okay, so fine. But the rest of this is actually the important part. So in order to be counted as a fantasy or simulation sports game, all winning outcomes must reflect the relative knowledge and skill of the participants and are determined predominantly by accumulated statistical results. Okay, so there's two important words there. One is skill and one is predominantly. Okay, so skill, this is the relative knowledge and skill of the players, meaning Mike and I, if we're playing the game, not the athletes. Like, it's how good are we at statistics in making our predictions? Okay, so the first question is, are we skilled at statistics and are the outcomes impacted by that skill? And the second is predominantly, which is, of course, a very wishy-washy word. There are different states write this in different ways. As far as I can tell, reading the Tennessee state law, there is no way you can legally exchange money in Tennessee, right? Like there's no luck can be involved in this. Okay, so people write this in different ways, but this is what the federal guidelines are. Okay, so they said, okay, if we give you all of our data, can you tell us if the outcomes of our games are predominantly determined by skill? And we said, sure, send us the data. So it turns out there's been a lot of work in this space, not in the context of fantasy sports, but particularly in the context of poker. So this is one of the best papers I saw in this. Is Texas Hold'em a game of chance? A legal and economic analysis. And if you look at the authors here, the first author here is Stephen D. Levitt. Does anybody know who Stephen D. Levitt is? Yeah. Yes, shout it out if you know it.
Freakonomics.
Freakonomics. He's the Freakonomics guy. Exactly. So he's the Freakonomics guy who also happens to like poker. And they wrote this beautiful article in the Georgetown Law Journal. And one of the reasons that this is great is that it treats the game as a black box, right? So a lot of the analysis on poker is like, okay, on poker, I can really just write down the probability of everything happening. And then you can start to combine all those things together. Here they said, okay, I don't actually care about the details of poker. I'm going to say there is some activity that happened, and I'm going to tell you whether or not this was luck played a role in this. Okay, so the first thing they say is in whatever activity you're doing, you should ask yourself these questions. So the first is, do players have different expected payoffs when playing the game? Okay, if there are different expected payoffs, it is not a game of luck, right? Because if you're flipping, so think of luck as flipping coins. If I'm flipping coins, if it's a fair coin, everybody has to have the same expected payoff, right? So that's a game of luck. Do observable characteristics of the player correlate with the payoffs they receive? Again, if an observable characteristic correlates, it is not a game of luck, right? So for example, like being tall does not help me in flipping coins. It does help me in basketball, right? So basketball, something other than luck is playing a role. Flipping coins, nothing. Do actions that the players take in the game have statistically significant impacts on the payoffs that are achieved? Also, like I can jump up and down all that I want flipping coins, it does not change the outcome, right? Whereas I can do things in basketball that change the outcome. And the one that I'm going to talk, so we checked all of these with the FanDuel data, but the one I'm going to talk about today is, are payoffs serially correlated, implying a persistence of skill? Okay, and this means if it is a game of skill and I'm good at it today, I will probably also be good at it tomorrow, right? Versus a game of luck, if I'm good at it today, that is in no way indicative of whether or not I'm going to be good at it tomorrow. Okay, so we're looking at for persistence of skill, and the first thing we did is we just plotted it. So this is I'm going to show you real data in a minute, but first we're going to do a thought experiment. Here's the thought experiment. I'm going to take all of my FanDuel winnings, all my FanDuel games, and I'm going to put a 1 for a win and a 0 for a loss. So I've got this long string of 1 1 0 0 0 1 0 1 0 1 1 1 1 0 0 0. I'm going to split it in half, and I'm going to calculate the win fraction for the first half, and I'm going to calculate the win fraction for the second half. Okay, and I'm going to put a dot on here for my win fraction for the first half, the win fraction for the second half. So maybe that's me right there, and maybe that's Mike right there, right? Maybe see so everybody here is going to be a dot. Okay, now before I show you the real data, we're going to do a thought experiment, and the thought experiment is the following. So suppose I could do the perfect experiment. Okay, and the perfect experiment is I have an infinite number of people playing an infinite number of games. Okay, I give you an infinite number of people playing an infinite number of games. All right, if that game is a game of pure luck, so it's coin flipping, what does this plot look like? I think be bold. Be bold. Dot. It's a dot. It's a dot. Exactly. It's a dot. It's right here, right? Because if I flip a coin an infinite number of times and an infinite number of people do this, everybody is going to win half of them and lose half. Right? So this is what it looks like if you have a perfect experiment with a pure game of luck. Okay? What if it's a pure game of skill?
Line of slope one.
A line of slope one. Perfect. Exactly.
I said that for the first one.
Okay. I ignored that one. So this is a line of slope one, because this is a guy who's bad at it here is also bad at it here. This is a guy who's good at it here is also good at it up here. Okay. Now, the reality is that I don't have an infinite number of people playing an infinite number of games, so this is noisy. So what I'm really going to get is something that looks like this, right? And so the math question now that I have to ask, this is the mathematical question that FanDuel asked me to answer, is my data more liney or more blobby? That's it. That's the math question. And there are lots of ways you can define liney and blobby, right? And so we picked one, and I'll show you what it is. But first, let me show you what the data actually looks like. So this is, I think, MLB or something, right? And you can't tell what this looks like because everything's piled up. So we're going to turn it actually into a heat map. So there's the heat map. Okay. And now I'm going to show you this for a bunch of different cases. Okay. So this is MLB, NBA, NFL, and NHL. The first thing I'm going to do is I'm going to show you what this looks like for people who have played 4 games. Okay, so people who have played 4 games means the first half of their season they played 2 games, second half they played 2 games. So that means for each half of the season, there's only 3 possible outcomes. You won both, you lost both, or you split the difference. Okay, that's it. So I'm going to show you what that looks like. So this is what that looks like. So this is lost both, won both, split the difference. Lost both, won both, split the difference. Okay. And you can see this looks like luck. There's a big bright spot in the middle of this. This looks more blobby than liney. Okay. And the reason this looks like luck, there's a great quote in the Stephen Levitt paper where he says the following. He says, even tiny differences in skill manifest themselves in near certain victory if the time horizon is long enough. Okay. And what that means is if you only play 4 games and somebody is slightly better than the other person, you can't tell that they're slightly better, right? Whereas if you play best 51 out of 100, you probably will be able to tell, right? So that's what this time horizon is. If you play enough games, you're going to be able to tell who is lucky and who's not. So in some sense, it depends on how many games everybody is playing. Okay, so we can do more games. So this is what it looks like if N is 16, this N is 64. I'm going to tell you a little bit about how we're going to do that, but now I'm going to tell you which is more blobby and which is more liney. And what we did is we just said, I'm just going to take the ratio of the variance in this direction to the variance in this direction. Okay, so if I'm a line, then the ratio of the variance in this direction to this direction is going to be 0. And if I'm a blob, it's going to be 1. Okay. And so first, let me just say I was very proud of this. And so I went to the FanDuel lawyers And I said, I got it. I've got your metric for you. It's beautiful. I said, I'm just going to take the ratio of those two variances. If B over A is skill, it's going to be 0. And if B over A is 1, it's going to be luck. And they looked at me with great sorrow. And they said, Peko, that will never work. And I'm like, why won't that work? They said, because if I take this to a jury, they are going to be super confused if skill is 0 and luck is 1. And so I said, that's a very good point. I have a new metric for you. It is 1 minus B over A. And then they were happy. Okay, so that's the metric we're going to use. So skill is 1 and luck is 0. Okay. And I'll just say, I'm not going to go through all the details since we have like 5 minutes left, but I'll say you can do a lot of really interesting mathematics with this. So you can assume that you've got sort of normal distributions. You can calculate what is the expected value of this from the real data. There's a paper on this in SciEm, which you can read. But I'm going to go on to the more interesting thing, which is the pop quiz, which is the following. Okay, this is the last slide in my talk other than acknowledgement. So this is your pop quiz. So one of the things you have to do, if you're gonna bring this to a jury, you can't say, my metric was 6.4 or whatever, or 0.64, because they don't know what that means. So you have to put it in the context of other things that people know. So what I did is I calculated that metric for a bunch of other things. And so we calculated it for real football and fantasy football, bicycle racing, real baseball and fantasy baseball, real basketball and fantasy basketball, the stock market, real hockey and fantasy hockey, and coin flipping. Okay, so now your job is to put these in order on this chart, and I will guide you through this exercise. So we will do the easy one first, which is luck. So which one of these is the most luck? Coin flipping, correct, yes. And it turns out it is 0, so we checked it. Yes, you do it and it turns out to be 0, so fine, good. Okay, next one on the next most one that's most luck on this. That is correct. It is the stock market. So the thing is, we looked at managers of 35,000 mutual funds, and again did exactly the same kind of analysis that we did for the athletes. And what I have learned from this is, do not buy a mutual fund. Whatever, they are overcharging you for it. Like people always say, buy an index fund. Buy an index fund. All right. So we looked at and we looked at over, I think, like 2 decades of mutual funds on this. Okay, so now let's go to this end. So which one of these would you put at the highest on the skill end?
Basketball.
Like basketball. Okay, I hear vote for basketball and for cycling. Yes, somebody want to argue for one of those? Cycling. I heard of cycling.
Cycling's less random.
Cycling's less random. Yes. So that is correct. It is cycling. And the reason for it's cycling is, in cycling, if you're fast, you're fast. Right. It's basically just a measure of how many watts can you put out. And maybe you get unlucky or you're tired on some day, but by and large, it's how many watts can you put out. Okay, now we are to the hard ones. Okay, and the first thing I will say is that the fantasy and the real sports are highly correlated. So I'm not going to have you try to decouple the fantasy sports. You just have to put the sports in the right order. Okay, and the reason they're highly correlated is I'm basically asking you how predictable is the outcome of these games, right? And so if it's highly predictable, then it's also easier to play the fantasy game. Okay, so what is the next sport that goes on the skill end? Basketball. Okay, I hear basketball. Football. I hear football. Yeah. Somebody want to make an argument for one of those for me? Yeah.
The best football teams lose 1 or 2 games a year.
Yes.
So their win percentage is highest.
Win percentage is high. Okay, that's a good one. Okay, good. Somebody want to make an argument for? What?
For basketball, you showed us some data already, and basketball looked the best.
Super mighty. Good. You were somebody was paying attention to my plots.
Also, to go with your quote,
Yeah.
Basketball, there's a lot more scoring opportunities. There's a lot more data.
That's exactly right. That's exactly right. So it is basketball for exactly that reason, that in basketball, there are a couple hundred scoring opportunities in every game. So one lucky shot does not matter, right? Whereas in something like hockey, one lucky shot can change the outcome of the game, right? And not only that, in basketball, there are 82 games in the season. So and football. So the reason football is not as high is there's only 16 games in the season. So 82 games in the season, hundreds of scoring opportunities per game, you get that. And I gave away what the other one was, on the other end. So the other end is hockey, right? So hockey, also 82 games, but very few scoring opportunities. And then in the middle is the middle. So there's where baseball and football sit. I will say, so I'll make two comments on this and then I'll wrap up. So the two comments I have is, notice that fantasy baseball is actually much higher than real baseball. So the outcome, so the skill is actually much more important in fantasy baseball than in real baseball, meaning in real baseball, there's more randomness than in fantasy baseball. And part of this is when you look at the data, there are people who are playing this for a living. Like you look, there are people who are playing 64,000 games a year and they're paying $10 a game to play, right? And so this is their job. And the people who are, and most of the people who are doing that are playing baseball because there's so much data in baseball. And so they have got like spreadsheets that they know what the weather is. They know if the pitcher's daughter was sick at school. They know whether they had cupcakes for breakfast. I mean, they know everything, right? And they're running algorithms. So there are people in that pool who have that level of information. And there are also people in that pool who are like, I like blue uniforms, right? And so when you put those two together, the people who have the statistical skill are going to win, right? So that's, I think, why baseball is so high over here. The one that I don't understand, which I think is actually really interesting, is this question about football. So this comes back to your question about football. Football, there's only 16 games in a season, which is very, so baseball's got 162 and basketball and hockey both have 82. So 16 is a really small number. So I'm surprised football is so high. And I suspect, well, actually one of my students pointed out, it's probably not the number of games you have to count in here, it's the number of downs. Right, so I think doing an analysis, thinking about the number of downs in football actually could be really interesting to understand why it's so high on this chart. And with that, I know I'm like 2 minutes over, so I'm just going to put up this most important slide. So these are all the people who were involved in this. Their names. So these are the folks who did the skill versus luck over here. Those are the folks who did the COVID one. And Ivan has just submitted the paper, so I don't have the paper out yet for the basketball, but hopefully that will be coming out soon. So if you are interested in learning more about any of these, you can take a picture of this, and that should give you the information for the 2 out of the 3 stories that I talked about today. And thank you for your attention. Questions? Question about skill versus luck. Stadiums, yeah.
So one question is, where does poker fall on that? Presumably there's some significant skill.
Yeah.
But then there's also, like, it very much depends on your data set, right? By your definition with blackjack, you can play it very badly and always lose, right? So then you could say it's a game of skill, but it's very easy to reach the optimum strategy. And by that metric, it's a game of luck.
Yes. Yes, that's exactly right. So I'm going to first say, we don't have quite the same data, but translating other studies of poker, poker is below these, but above, so poker somewhere in here, right? But you're exactly right that there are, there's 2 interesting knobs here. So the first one is that your playing population matters, right? So if I had, if I have 2 people playing golf and one is a professional golfer and one has never held a golf club, the person, it's a matter of skill who's going to win that game, right? If I have 2 professional golfers playing against each other, now there's a lot of randomness, so there's more luck involved. So the distribution of skills in your playing population matters when you do this metric, right? So that's number one. And there have been talk in fantasy football or in all these fantasy sports about, should we actually have 2 different playing populations? Should we have the people who are doing it professionally and the people who are just playing it for fun? Okay. There's a whole long legal story around that, which I'll come back to in a minute. The other thing that's really interesting about this is that, so let's say you were actually FanDuel or DraftKings, and the government comes to you and says, sorry, that your game is too much luck. We're going to shut you down. So there is a knob that you can turn, which is that, remember, the way you get good at this game is you have to beat whatever that computer is. You have to find the people who are undervalued, right? Okay. If the computer values everybody perfectly, it is completely a game of luck, right? Because you can't be better at spending your $25,000 because everybody has the same expected value, okay? So the good news is, in order to make it a game of skill, your computer algorithm has to get worse, not better, right? So all you have to do in order to turn this more into a game of skill is turn up the noise in your pricing algorithm. And if you turn up the noise in your pricing algorithm, now this suddenly turns into a game of skill because now there are bargains that people can find. So there are not, if you are actually wanted to do this for if you want to start a company, there are knobs you can turn to sit anywhere you want on the spectrum. And then the last thing I'll say about this is that games tend to be around here. So there is this, so first of all, sports are entertainment, right? And there is a sweet spot for where you want to be for entertainment, right? So you don't want something like if the outcome is a foregone conclusion, nobody's going to watch it, right? Because then you're too far over here. But if it's random, so that the skills of the players are not rewarded, then you're too far over here. And again, nobody's going to watch it. So there is a sweet spot over here, which I think the leagues can dial their rules in order to sit in this sweet spot to make it more attractive for people to watch the games. Yeah.
Is this a problem? Something you hear about in basketball recently is that there's too much skill, that offenses are too good. And it's interesting that basketball is all the way on the skill side of that spectrum. And so the league might be trying to think of ways to dial that back and introduce some more law.
To make it more, yeah, this is a great question. So I have had more conversations with baseball than with basketball, but I agree with you that basketball is so far up here that they may need to do something to move this way. But I will say this about baseball. So MLB is actually terrific. Like every year, they are looking at all of the data about who's watching the games, why are they watching it, why are they not watching it, what can we do to get more into the sweet spot over here, and what can we do to make it more attractive to fans. The thing about baseball is that they've learned that 4 hours is too long for a baseball game. Nobody wants to sit there for 4 hours. So I will say this, one of the recommendations we gave them, put in a pitch clock. You're welcome. You're welcome. Totally changed the game. It's great. Yeah. So, but all of the leagues do think about this, and they are willing to change rules in order to get things more enjoyable for the fans and safer for the players. Yeah. So I can, and then here and then.
So I do not have any thesis about this kind of thing, but I have two quick questions. First of all, is it possible to locate the index fund in this row? That is the one quick question. And then the second one is now people are saying maybe there is no basis, but they are saying that maybe there could be some kind of chances to change that mutual funds location by using machine learning or something like that.
Actually, that's a good point. So this mutual fund, this was all based on people. So it is absolutely true that if there was somebody, so because we did this average over a large population, if there was a small subset that actually had, if it was a small enough subset, so if there were a significant number of people who were doing better with algorithms, it would pull that out, because then the people would be doing worse than the algorithms. But because we did this before there was a lot of sort of I don't know the trajectory of sort of of AI in mutual funds. But if we did this before the AI burst, then it could be that if we ran this again, we got something different. Yeah, interesting. And index funds. So index funds. I think index funds I don't think we could actually do index funds on this, because the metric we said is do you beat the market, right? And index funds are the market. So yeah. There's another question. Comment over here. Yes. No. Maybe. No.
I had a question about so for sports, it's like a volume game, right?
Yeah.
You want to get as many eyes on it, people in the stadium. Like in a game like online gambling, like if I'm gambling against you, I don't really care about I just want how much money I make.
Yeah.
So do you know enough about that business? If are they interested in getting in the sweet spot, or do they have competing kinds of?
That's a great question. So I think, as far as I can tell from my conversations with FanDuel and DraftKings, they would like to stay on the right side of legal. That's the first thing, right? And the right side of legal means you have to be somewhere up here. Because, and it's hard to see from this, but if we do it run it with more data, these are actually pretty kind of closer. So I guess they don't have, yeah, I see where because you could actually dial up the noise and say, oh, okay, yeah. So there is one thing that they may want. So they have a population that is just playing for a living, and those people want to be up here because they're good at it and they want to be predictable, right? So they just want to know, okay, my algorithm is great and I want you to pay me for my great algorithm. There are other people who are like, okay, I'm going to my 12-year-old birthday party and we want everybody to have a chance to win, right? And so if everybody has a chance to win, then you want to be down here, right? So I think it depends entirely on the playing population, and it probably depends on, and they probably actually need both of those playing populations, because these guys are dumping a boatload of money into the system, but there's a lot more people down here. So it's not obvious to me where they would want to sit on this. Yeah, other than on this side of legal. So, yeah. Right. Yeah.
I was curious, the basketball, the first story. So you were looking at made shots.
Yeah.
I was curious if you looked at another opportunity, which is rebounds.
Oh, yeah.
And looking at, like when the shot goes up, where are the people and who is able to get, position themselves better for obtaining a rebound. Because they, like years ago, they had made a big deal about Karl Malone would like studied how the ball would
exactly. He
hit
would
the rim and he would position himself,
yeah,
accordingly. So
we have not done that, and that is a great idea. I will call you when I have a student who's ready to do it. We will write that paper. That's great. Yeah.
Actually, two questions from
on
Zoom.
Yeah.
So one is, do the participants' beliefs about the relative importance of luck versus skill matter?
Do the participants in what?
Beliefs.
In the game.
About the relative.
Oh, in the game, like a basketball player.
It says participants, so I don't know.
Okay. Yeah. Okay. So it could be, yeah. So I would say, okay, when I talk to people who play fantasy sports, they say it's all skill. I'm good because I'm good. Oh, and actually that one that I just screwed something up on that one that I lost. Okay. So people believe, people believe that they're doing something. For the athletes, so I haven't talked to the professional athletes, but I will say we've worked with a lot of the MIT athletes. And they are a really interesting population because they are used to getting critical feedback to improve. And part of that is because they know that on some days you lose and on some days you win, and the more prepared you are, the more likely you are to win, but then sometimes you will still lose. So I feel like the athletes that are immersed in this, I feel like they have experienced so often, most of the time we were prepared, we won because we were prepared, but sometimes we got unlucky. So I think this actually resonates with the athletes. With the fantasy players, I think everybody believes they're up.
There's another question. So how will the matching mechanism influence this? Wait a minute. Sorry.
Yeah.
For example, if you win a game, then you need to play against a better team. Will this change the distribution of the plot?
I see. Oh, I see. Okay, so I'm not sure I understand, but let me try. So, well, we're currently in the middle of March Madness, which means if you win, you're going to go and you're going to play a better team, right? So all of the data we did here was not postseason data. This was all in regular season. So the schedule is set ahead of time, so it's as random as you can make it. But that's absolutely true that if you did this with postseason, it would certainly be biased because only it's win or go home. So yeah.
One could say that the football schedule is also set where better teams are pitted against better teams from year over year. So
yeah, and I wonder if that's also why this is higher somehow. I'm not 100% certain on that. But I feel like the football is kind of a weird one on this again because you have so few games that you have to try to make the most of all of the games that you do, and the league's incentives for what make the most of may be different than like the team's incentives for what make the most of. Yeah. Yeah.
Did you ever look at, for the basketball data on the defensive side, when it might make sense to foul out the other team to stop them from scoring when there's a really high expected point value?
Oh, that's a great question. Actually, that's the other paper we're going to write. because that one you as far as you could absolutely use that as a decision-making metric to say what was the probability of score of what was the expected value of the score, and is it more or less than what you gain by the foul. That's a great, we totally would have the data. We would totally have the data to do both of those. Yeah, it's great. But we haven't done it yet.
Actually, maybe we should stop the official questions now because we actually have a reception going, so you can still ask questions there.